Hi, in this video, we're going to take a look at using linear regression for supervised learning. Okay, so linear regression by far is the old school granddaddy OG of predictive modeling. Now, linear regression is mathematically the simplest model we possibly could have. It's very simple that I have like numeric value times coefficient, add them all up, add on an intercept or a bias, however you want to call it, and that gives me my value. And so this point of view has tons and tons and tons of features to it. Also, it's fast. It's really fast because of the matrix algebra connection between linear regression and matrices. Um, So this is a super, super, super powerful approach to predictive analytics. Now, honestly, it's usually not the most powerful predictor, but I personally use it for every single regression project I'm on. I will always do a linear regression model and I will do a single decision tree model also at the beginning of the project to give me a better understanding of what's going on because they're so easy to interpret, so easy to understand, they can guide me through things. Now, linear regression also has a ton of hypothesis testing available to it. And so we can get deeper results from a linear regression model than we can in other predictive analytics models. Also, really, if you want to understand all of the pitfalls and shortcomings and problems with data that come up during predictive analytics, easiest way to understand it is using linear regression. Regular linear regression, because of the matrix aspect of it, we have so many more tools to be able to understand what's going on. And because of that, I can truly understand other aspects like overfitting. Like, why is overfitting a problem? How do I identify overfitting? Well, you know, it's easier to understand in a linear regression point of view than it is in like a neural net or a decision tree or random forest or something like that. And so I suggest every single project you work on for regression, you start with a linear regression model and you start with a single decision tree model also. All right, so linear regression is the foundation technique in supervised learning. It provides a straightforward and interpretable model for us, very easy to interpret. Inference is good. So now it's not going to be the strongest predictor most of the time, but it still does a pretty good job given that we consider that we get so many other things for free from it. It is super interpretable because of the matrix algebra aspect of it. All right, so the basic concepts of linear regression, the goal is to model the relationship between the dependent variable and one or more independent variables. The goal is to find the line of best fit or hyperplane higher dimensions that best fits the data. Now, when I say fits the data, I'm talking about ordinary least squares. When I say line of best fit, I want the line that minimizes the sum of squares error or hyperplane that minimizes the sum of squares error. Now, advantages. Oh, it is fast to train because of the matrix algebra connection. It's mathematically simple. The equations behind linear regression are the simplest you're going to get anywhere in predictive analytics. There are special formulas and special tools for linear regression that we don't have for other type of modeling. So, for example, there's a leave one out cross validation formula that makes leave one out cross validation like for free with regression that we don't have for any other model structure. The theoretical foundation is second to none. It is well developed. We understand it truly. I firmly believe that if you are going to be a good modeler for predictive analytics, you need to first get good at linear regression. That will guide you in all other projects. Good data prep for linear regression is good data prep for all models. Interpretability, the parameters of the linear regression model, the coefficient says, makes it easy to interpret what's going on and gives us insights into what's going on. Also, because of that interpretability, I have an easier time spotting if I'm overfitting my model by having redundant predictor variables. Statistical inference, nothing even comes close to linear regression for statistical inference and benchmark model. I frequently use this as a benchmark to compare other models to see how much more of an improvement I get, because usually linear regression is not my most powerful model during my projects. Now, disadvantages, and there are a few. It's sensitive to outliers. Or outliers can greatly influence the line of best fit. In contrast to something like random forest, if I have an outlier, it gets put off in an extreme leaf, but it gets that leaf I ultimately have averaged out with other extreme outlier values, and so it tends to not be such an issue. Data preparation. The model's performance is heavily reliant on how well we prepared our data. Also, overfitting. With a lot of features, I have a risk of overfitting. Now, this is true for any type of modeling, but it's easier to articulate and understand it here than with other types of models. Also, there's no variable selection, so we have to do variable selection either with like forward selection, backwards elimination, stepwise, or using subject matter knowledge. Do a correlation study on what's going on. So, there's no direct, immediate variable selection process. I have to invoke some other tool that's related but different. And also, the model formula has to be identified in contrast to other model structures that will go through. And as long as I don't have too much junk in there, we'll go through and figure out what the predictor variable should be of what I gave it. Now, the assumptions of linear regression. Now, we have a lot of assumptions. We actually don't need all these for prediction. I need all of them for hypothesis testing. If I'm not interested in hypothesis testing, I can actually weaken this by quite a bit. All right, so here, linearity. So this is just saying I have the right equation. So I'm making the assumption I got the equation right. Independence, observations should be independent of each other. Now, there are techniques to deal with this if I have a lack of independence for certain situations. Go look at my linear regression, videos if you're interested in that. Homoscedasticity, we make an assumption that the residuals or the errors of predictions have constant variance with respect to the predictor variables. We have normality of our errors, independent, identically distributed. Normality, mean zero, standard deviation of constant, and we have no multicollinearity. So I don't have any redundant predictor variables. All right, for the purpose of prediction, I only need linearity and independence. We don't really worry about the other ones. We still would have to have an expected value that makes sense for it, which is really not a high bar. But the last three are strictly focused on hypothesis testing if I want to be able to run things there. All right, so let's take a look at simple linear regression. Simple linear regression is definitely where you should start learning predictive analytics. I've got one predictor variable, one target. It's as easy as possible. Here I have an intercept, the y-intercept, just like in middle school algebra. Here I have a coefficient of the predictor variable, and this accounts for all aspects of my model that don't account for what's going on in the situation. So the epsilon term is my error term. This accounts for everything that is like missing from my data that should be in that's actually impacting what's really happening. Now, multiple linear regression, we just go through and we have more predictor variables going on and coefficients. Now, I can put this into a matrix formula right here. And so here I've got the predictor variables times the coefficient vector plus the vector of errors. And now the classic formula for this beta is going to be that should be beta hat, by the way. I'll fix that later, but this should be beta hat. It shouldn't be beta. That's a mistake on my part. So here, this is the formula for fitting this. Now, this formula, you'll notice it has a matrix inverse in there. So something that has to happen for this matrix inverse to exist, X has to be a full rank matrix. So our predictor matrix, which will include a constant for the intercept, has to have full rank. Now, you'll notice that when I run scikit-learn, I can still run it without full rank matrix. Now, the reason for that is because there are numerical linear algebra techniques, that I can use that will give me exactly the same coefficients when I have a full rank matrix. But with those other numerical linear algebra formulas, I don't have to have the inverse exist. I'll still be able to get a model. There are still problems with that. You don't want to do that. Do your feature selection. Scikit-learn will run and give you the output, even though you're doing something stupid. You want to make sure that your predictor variables form a full rank matrix across the board, no matter what you're doing. Because if it's not full rank, that means that you have a redundant predictor variable, which means that you're going to have instability in your parameters, which means it's going to take longer to compute and train and just fit your data. And it's going to make interpretation harder. And also, that variable, the addition, redundant variables are also an opportunity for problems down the road when, let's say, your organization stops like recording a data field. And if you were using that in your model, well, now you got problems. Another problem with linear regression I did not put in there is that it can't have any missing values. There are certain implementations of tree models where it's okay to have missing values. Linear regression cannot handle missing values at all. All right, now for model fitting, the estimated coefficients in linear regression aim to minimize the sum of squared errors. While the matrix formula is mathematically correct, directly using the inverse can cause numerical instability, especially when some of the predictors are collinear. That means I have redundant predictor variables or nearly redundant predictor variables. There are more stable algorithms in numerical linear algebra to fit a model, but we're not going to talk about that here. We just need to know that they exist, and scikit-learn is actually implementing them under the hood. And so as long as I have a full rank matrix, what's going to end up happening is I'm going to get the same coefficients. It's not a problem. If I do good, solid feature selection, it's not going to be a problem either way. But this formula here, sets it up for us to be able to work on the theoretical aspects of regression. All right, so let's go through and run through an example. So here I'm going to use the house prices advanced regression techniques data set once again. I'm using PyArrow to speed things up, and by setting up a data type dictionary, I can speed things up. Also, you can slow it down. It would have been better if I would have gone through and specified exactly like integer 32 and stuff like that by specifying the amount of memory. That'd be more efficient, but I'm a statistician, not a computer science person. I really don't care. Okay, so now I'm going to organize my predictors. I do this at work. I was doing this today. And so what I'm doing now is that I'm going to have two different models. I'm going to show you a full model where I use everything in my predictor variables. I'll use all of them. And also I'm going to do a reduced version where I did a feature selection to minimize the set. And I want you to notice the output when it comes to the mean squared error. So here you'll notice that I've got all of these predictor variables that I'm going to throw in there. Okay, I didn't do any feature selection. I'm just going to run with it. And here I've got a reduced list of predictor variables. Okay. And so now how I'm going to proceed is I'm going to put my predictor variables into a list. So I have a list of predictors, which is list full and list reduced. And I'm going to use the list notation of for loops to kind of speed things up. I like keeping everything organized into individual like lists. So one thing I like to do when I have multiple models, I like to have them all in a list. That way I can iterate over any operation I want to do. If I want to get the fitted values from each model, if I want to check, the validation statistics, having things in a nice compact list makes things programmatically easier for me to work with. All right, and so I'm going to do that here. All right, so now what I'm going to do is I'm going to actually fit my model, and I'm going to take the predictor variables that I have, and I'm going to go ahead and I'm going to fit linear regression models for each set of predictor variables I have. And you'll notice I'm running a nice compact for loop for me, and it's immediately stored in a list for me. I like this a lot. And the result is I have two fitted models that are linear regression models. Okay, so let's get the coefficients for for our two different models. All right, when we center and scale our numeric predictors, we can use the coefficient magnitudes as feature importance, but I have to have things rescaled, preferably centered and scaled. Honestly, there's no theoretical reason not to center and scale your data. You'll end up getting the same prediction values either way. That is a result in another one of my linear regression models videos. But so here I've centered and scaled before this video when I did my data prep. Mean 1 for all numeric predictors. Standard deviation is 1 for all numeric predictors. Now here, dummy variables have a different interpretation, but we can also use their coefficient magnitudes. Just keep in mind that we interpret things differently. The coefficients, if I have all my assumptions met, the coefficients tell me if I increase a predictor variable by a certain amount, I would expect on average to see that coefficient's proportional increase or decrease, depending on sign, in the target variable on average. All right, now when the numeric predictors are not scaled to 1, we need to use the t-test to evaluate predictor importance. And as far as I can tell, this is not supported by scikit-learn, and we're not going to talk about it here. That's more of a theoretical point of view. I strongly recommend that you center and scale your predictor variables. Scikit-learn makes it super easy. Go with it. By default, the exponential transforms in scikit-learn center and scale. So, I mean, it's just done for you for free. It's nice. All right, so now, if I check this out, the full model is overfit with too many predictor variables. Think of it like this. I had a soup, and I was cooking, and I threw in every single ingredient I had into the soup. And what ends up happening is I have junk soup that does not taste good. Nobody wants to eat my soup. Or you can think of it as I have too many cooks in the kitchen ruined the soup. Either way, I threw in everything just to throw it in, and I got burned. Okay, so do your feature selection. All right, so how can I use the coefficients to identify that I've got overfitting? Well, first and foremost, coefficient signs need to make sense. All right, if on average, things should go up. If I increase a particular variable, I would expect on average for the target variable to go up, and I see a negative coefficient, something has gone wrong. Also, if I would expect things to go worse, if I increase the predictor variable value and I see that the coefficient is positive, it's going in the wrong way. So for example, if I have a high quality exterior for a house and the coefficient is negative, that's bad. Something's wrong. So having a higher quality exterior should increase the sales price. But my model is saying, hey, for the full model, it is giving me a negative coefficient. That is saying that the exterior quality, as it goes up, we would expect on average for things to go down on the price. That doesn't make sense. What's happening is that the model is working to give me the line of best fit or hyperplane of best fit. And what it's doing is that one predictor variable is going too big in its coefficient, and another predictor variable is going negative to counteract, so that together they average out, but they only average out on the training data. All right, it only averages out on the training data, not on the validation data, not on the test data. And so if this was a real life project, I would hit the brakes right now because I checked the coefficient. This is, really good. Now, another one that I want to check is the magnitude of the coefficients. If I get something huge, then it doesn't, like, that doesn't make sense for what's going on. All right, so I've got multiple e to the 11 for coefficients. That is a huge, huge, huge number. That magnitude does not make sense for my target variable. Remember, I have a variance of 1 for all my predictor variables. So really, I would expect things to be more similar in magnitude, maybe one or two off from each other. And so here, this is absolutely ridiculous. All right, so what's happening once again is that this value is going super, super big, and another value, maybe this one, is counteracting it, and they're averaging out on the training data, but that only applies to the training data. It doesn't apply to validation. It doesn't apply to test. All right, and so here, now when I look at the reduced model, I see things, that look more in line with what they should be. Things are relatively the same magnitude. There is a little bit of variation, but it's nothing like grossly wrong. And so now I didn't do it here, but for a real life project, I would go through and make sure that the sign of the coefficients makes sense before I would put the model in production. Oh yeah, and so here, let's look at, so we can do it right now. And so when I see low for a dummy variable, so this is, I went through, did binning by higher sales price, moderate sales price, and low sales price on each of my predictor variables. And I expect the ones that have low to have a negative coefficient. That makes perfect sense. I would expect the ones with high to have a higher coefficient. This is why I like this format for my for binning my predictor variables. Also, if my ground living area is larger, I should expect to see higher sales price. Well, hey, right there, I have a positive coefficient. Neighborhood is high, associated with higher sales price. Boom, that works out. Overall quality, higher quality, I would expect to have a more of a sales price. And so things are looking pretty good. So I feel good about the reduced model. I don't feel good about the full model. Now, if this was a theory class or a classic statistics class, we would go ahead and start talking about ANOVA and other hypothesis tests. Here, we're trying to set ourselves up for other types of modeling, or where we're more focused on predictive analytics, where we're focused on any type of model structure. And if I'm doing any type of model structure, well, I don't have ANOVA to work with, more than likely. And so now let's go ahead and start using some of the features that are in scikit-learn. We can get the rank of our predictor matrix. So we see 102 and 41. We can also get the singular values from our predictor matrix using .singular underscore. And so for here, one thing that you want to look at is, do I have any zeros, or very, very small? Notice I rounded it off to make it easier to interpret. If I have any zero singular values, strongly consider reducing my features. You go back to my feature selection to reduce it down. That matrix formula that I showed you a moment ago for estimating beta hat, if I had any zeros in my singular values, that formula will not run because I will not have an inverse matrix as needed. But now this just kind of shows you that we're not using the actual classic formula. We're using a different numerical linear algebra approach to fit our model. scikit-learn will fit a model even when it's not full rank. All right, so in that situation, it's a bad idea. You need to go back to your feature selection. Yeah, the singular values are used in the matrix algebra of fitting the model. And now if I look at the reduced model, you'll notice I don't have 0 in there. I'm using a full rank matrix, and I feel better about the reduced one. All right, now here, check out the intercept. Look at this, is ridiculous. This is a ridiculous value. The full model is junk. Now here, maybe it might be reasonable. I don't know. We'll figure it out. Now, number of predictors. And so here, you notice I got 147 and 41. Compare that to the rank 102. That's going to correspond to the number of zeros in my singular value decomposition. And 41, and I've got 41 as my rank. It's not a coincidence. Now we can get the predictor names by using dot feature names in. I can get all of the predictor names. And now to get the fitted values, once again, I'm just going to use the list for loop notation, use the predict function. Now here, when I get the results off of this, I'm going to need to take the transpose of it. And then, I name the columns. And so now I'm going to just start, doing some data manipulation. That way I'll be able to set up, a data frame that'll have the predicted values, and we'll have like which model and the residual and squared residual. So here's the actual value that I want to have. Here is the partition that I have for training, validation, or test. Which model is it, full or reduced? Reduced is at the bottom, as you can see here. Here's the actual predicted value. So remember that sales price was transformed using Yo Johnson and then centered and scaled. Here's the residual between target and predicted. I like to put my residuals as predict minus sales price, because when I see a positive residual, I know that my predicted value was larger than my sales price. And here is the squared residuals. All right. And so now I can go through and very easily, using the group by function, get my mean squared error for both models and for each partition. And so now check this out. Let's look at the train first. All right, I've got 0.08 and then 0.11. Okay, so the reduced model has a larger training mean squared error. But now check out validation. Here I've got 0.12, but reduced actually has a lower validation. It actually did better with fewer things added in. Doing your feature selection will improve your model. Let's look at tests. For the full model, I've got 0.14. For test on reduce, I've got 0.1. Once again, I have a better result. All right, now, something else I want to check. If I see a gap between the train and the test, or train and validation, that's an indication I have overfitting. Well, you know what? There is a difference here. Now, it's going to be normal for training to be the best no matter what you do. So expect for there to be a gap. All models overfit on their training data, but you'll notice that, here, if I round that, that's 0.11. Here, I round it, it's 0.11. That's pretty tight between train and validation. Now, here, a little bit of difference between test and train. Test actually did better. It typically does worse. And so since, if I see that test is actually a better score than train, I'm not worried about overfitting. It's, but here I see that test has a significant difference between train. That's a sign that I have overfitting. All right, so now let's go ahead and visualize the predicted value by our target variable. This is our #1 most important visualization for any regression model, is that I'm going to go through and I'm going to just plot my predicted value by the actual value that I'm supposed to have. And now I'm also going to do this for train, validation, test, and for both models, full and reduced. So here I have the full model on the training set. I have the full model on validation. Notice that it's going to be a little bit more dispersed out in here, and then I have it on test. And you'll notice now, this is also a good way for me to find possible outlier values that I did not sufficiently address earlier. And we can keep going through this, scrolling through. Now I can use Seaborn to put everything onto one plot, real easy peasy, lemon squeezy. And I can go through and we can see that the full model, it's a little slightly tighter here, especially in the extreme values. Like, yeah, we have more extreme values in the reduced here than we have over here. But when I start looking through, things are going to actually end up being better. You'll notice I don't have anything sticking out very far. Also, when we interpret this visualization, this point here corresponds to, we have to go vertical to check the error. The error is not, it's not 90 degrees to the line, it's vertical to the line. And so this is a decent error right here. This is a decent error. This is also a decent error. Well, I don't have as big of drops. So on the reduced model, on validation and test, things did better at avoiding like the big mistakes. Now we can also visualize the residuals by our target. And so I've got the target variable value, and the vertical is the residual value. And something that is important is I don't want to see a trend. If I see a trend, if I can, like a circle, a line, a hyperbola, anything like that, that's a sign that there's something that I've messed up on. Now here, you could see that possibly there's a line going, possibly. It's, to the right, we notice that we've got negative residuals going on. So maybe something going on. When you look at this, if you can move, delete, or add one point and contradict what you see, you don't see a trend. And so if I was to put one point over here to contradict it, it would look better, but maybe there's something lacking in my model. Maybe I'm missing a variable. Maybe I should do maybe a transformation on a predictor variable. I don't know. Feature engineering, something like that. Now we can also visualize the squared residuals. And the reason why we do this is that we want to spot the ones that are deviating a lot and double check to make sure that there isn't something going on with my data. Notice I don't have anything big sticking out when it comes to my reduced model, but I've got some things sticking out in training and validation of the full model. And there will always be like a highest point, so don't fret about it. But you can see that the highest ones were already with the model that I've concluded is not trustworthy. Now we also wanted to visualize the distribution. We only need to do this if we are going to be doing hypothesis testing. If I'm doing hypothesis testing, I need those assumptions, specifically that normally distributed of the residuals has to be there. Independence between the observations and constant variance with respect to the predictor variables. All right, and so I can look at the distributions, and so we can we can notice some stuff that's going on. Now let's visualize the QQ plots. This is another way to check the hypothesis of normally distributed. And now here, when I look at this, I notice that specifically on the right, on all of them, it's too big, it's above the line. So here I'm seeing larger values than what I would expect to see given if things were the normally distributed. And so there's some issues going on here. And so you'll notice that I've got something like these guys over here that are sticking out to the right are the ones that are going to be sticking out over here. Also, there's a little bit of deviation on the left-hand side on the training. I think that's okay. This over here, this is definitely a deviation that that deviates from normality. So the full model is going to be one that I wouldn't really trust for hypothesis testing. While things, the left-hand side at least looks a lot better. Honestly, reduced model, this is enough that I would be like, I would like to avoid hypothesis testing if I could. Maybe I can't, depending on my project. But at least I would be well informed on what's going on. Okay, so for your homework, pick a data set you're interested in. Fit a simple linear regression model that has one predictor variable in there. Fit a multiple linear regression model with all your predictor variables. Assess your coefficients to decide if you need to eliminate predictors. Generate the visualizations that I generated above. And now do it again, this time using lasso or ridge instead of linear regression. These are going to be similar models, but they're going to establish the coefficients by a different mathematical method. The simple linear regression, multiple linear regression works to minimize the sum of squared difference between observed and predicted. Lasso and ridge use a different mathematical format, which we'll talk about later. I want you to compare the coefficients between your penalized model, lasso or ridge, and your linear regression model. All right, well, that's all I've got for you. Life is short. Do math.